Let's understand electromagnetic waves in this video. Have you ever wondered how light, radio, and mobile signals travel through empty space without any wires? Think about sunlight reaching your eye and a radio playing from across town, both carried by the same basic idea. Maxwell gave us that idea with four simple laws that link electric and magnetic fields. First, Gauss's law for electricity says the net electric flux through a closed surface equals the total charge inside divided by epsilon naught, where epsilon naught is the permittivity of free space. Second, Gauss's law for magnetism says the net magnetic flux through a closed surface is zero, which means there are no isolated magnetic charges. Third, Faraday's law says a changing magnetic field makes a circulating electric field, and this is how generators and transformers work. Fourth, Ampere's law with Maxwell's addition links the magnetic field around a loop to both the conduction current and a new term called displacement current. Why did Maxwell add displacement current? Because charge must be conserved, and the original law did not always match that requirement. The continuity equation says the divergence of current plus the time rate of change of charge density equals zero. So Maxwell added a term proportional to the time rate of change of the electric field. We call the displacement current density J sub d, and it is the partial derivative of d with respect to time, where d is the electric displacement. In vacuum, d equals epsilon naught times E. So a changing E field gives a displacement current that creates magnetic effects even where no charges move. Picture a charging capacitor. Current flows in the wires but not through the gap. Yet, the changing field between plates produces a displacement current which makes the same magnetic field as the wire. This fixes the math and gives symmetry between electric and magnetic fields. Now, electromagnetic waves come from time-varying electric and magnetic fields that sustain each other and move through space. A simple plane wave can be written as E equals E naught sine of omega times the quantity t minus x divided by c, and b equals b naught sine of the same phase. Here omega equals 2 pi times the frequency and c is the wave speed. Key point E and B change sinusoidally, are at right angles to each other, and are both perpendicular to the direction the wave travels. So these waves are transverse. The speed of electromagnetic waves in free space is c equals 1 divided by the square root of mu naught times epsilon naught, where mu naught is permeability of free space and epsilon naught is permittivity of free space. Also, the ratio of the maximum electric field to the maximum magnetic field equals the speed c. So, c equals E naught divided by B naught. The energy in an electromagnetic wave is shared equally by the electric and magnetic fields, and the flow of energy is described by the Poynting vector S equals 1 divided by mu naught times the cross product of E and B. Intensity is the average energy crossing a unit area per unit time, and for a wave it relates to E naught squared times epsilon naught and c. Electromagnetic waves cover a wide spectrum from radio waves to gamma rays, and different parts have different uses, like radio for communication, infrared for heat sensing, and X-rays for imaging. Let us look at some solved examples to make this concrete. Question number 1 asks, calculate the frequency and wavelength of an electromagnetic wave with an energy of 6.626 times 10 to the minus 19 joules. Use Planck's relation E equals h times f, where h is Planck's constant, 6.626 times 10 to the minus 34 joules second. Solve for frequency. F equals E divided by h. So F equals 6.626 times 10 to the minus 19 divided by 6.626 times 10 to the minus 34, which equals 1 times 10 to the 15 Hertz. Now wavelength lambda equals c divided by f. So lambda equals 3 times 10 to the 8 meters per second divided by 1 times 10 to the 15 Hertz, which equals 3 times 10 to the minus 7 meters. Question number 2 asks, what are the applications of X-rays? X-rays are used in medical diagnostics to see bone fractures and other internal problems. And they are also used for ionization-based studies and inspections. Question number 3 asks, are X-rays and gamma rays suitable for broadcasting radio or TV signals? The answer is no. They are unsuitable because they travel short, useful distances for communication, and their high energy is harmful to living tissue. Question number 4 asks, which is not a property of electromagnetic waves among momentum, energy, pressure, and heat energy? Electromagnetic waves can carry momentum, they carry energy, and can exert pressure, but they do not carry heat energy as a separate property, though they can heat objects when absorbed. Question number 5 asks, a sunlight ray produces a color that registers energy 4.0 times 10 to the minus 19 joules. Which color is this likely to be? Use E equals H times F and solve for frequency. F equals E divided by H equals 4.0 times 10 to the minus 19 divided by 6.6256 times 10 to the minus 34, which gives approximately 6.03 times 10 to the 14 Hz. Convert to wavelength, lambda equals 3 times 10 to the 8 divided by 6.03 times 10 to the 14, which gives about 5.0 times 10 to the minus 7 meters or 500 nanometers in the green part of the visible spectrum. So what do we learn from this? We learn that Maxwell's equations tie electric and magnetic fields together. Displacement current completes the symmetry, and time-varying fields make electromagnetic waves that travel at speed c. Let us quickly remember the main points. 4 Maxwell equations, the role of displacement current, waves are transverse and travel at c, and the spectrum has many practical uses. So today we learned how fields make waves, how to get frequency and wavelength from energy, and why displacement current matters. Keep exploring these ideas with simple problems and diagrams. Practice the wave formulas and remember the physical meaning behind them. Thank you for listening. Keep studying with curiosity, and you can find more clear lessons and practice on EduRev to support your learning.